Hello, everyone. My name is Charalampopoulos, and I'm a PhD student at DTU Space in Copenhagen, working under the supervision of Yorgos Leloudas. My research field is transients and specifically tidal disruption events. And I'm ready to submit a paper on a spectroscopic population study of tidal disruption events. And this is the work that I will present here. But first, let me make a quick introduction on tidal disruption events, and abbreviated as TDs. Although Ioannis Liodakis before made an excellent introduction, but it was another session, so I'm going to do the same. So what is a TD? We believe that in the center of every active galaxy lies a supermassive black hole. And when a star orbits around a supermassive black hole and gets closer than the tidal radius of the black hole, which is defined as this, it gets torn apart by the immense gravitational force of the black hole. If the black hole has masses between 10 in the 5 to 10 in the 8 solar masses, then the star gets disrupted and we have a TD. If the black hole is heavier than 10 in the 8, then there is no disruption and the star supposedly gets swallowed whole, so we don't have any flare to observe. So around half of the stellar debris escape the black hole in unbound orbits, and the rest starts circularizing and falling back to the black hole in bound orbits. Supposedly matter falls back as a stream which self-intersects, soaks, and then steadily creates a rotationally supported accretion disk that starts getting accreted in the black hole. And both stream socks and radiation from the accretion disk produce electromagnetic radiation. And this is the process that our telescopes observe that gives rise to the tidal disruption flare. And sometimes it is so luminous that it can outshine the galaxy that embeds it. And so when the TD happens, this illuminates the nucleus of the host galaxy. As you can see here, this is the reference image, and this is after the TD has happened. And this is an event from 2019. And the wide field surveys like PanSTARRS, ZTF, or Assassin trace these transient flares. Okay, some basic properties of optical and UV tidal disruption events. And that is what this work studies. I'm studying optical and UV TDs because they have been also observed in the X-rays or in both regimes. So they are well characterized by a blue continuum, which is supposed to peak at the extreme UV and X-rays. Their continuum was supposed to be dominated by broad hydrogen and or helium lines, that emission lines that generally have widths corresponding to velocities of 10 in the 4 kilometers per second. And most of the times the line widths narrow over time as the luminosity drops, in contrast with AGN studies in AGNs the lines supposedly broaden with time. And after fitting individual events, spectral energy distributions, we know that they have photospheric radii spanning from 10 in the 14 to 10 in the 15 centimeters, and where the photosphere recedes with time. And they also have black body temperatures of around 10 in the 4 to 5 times 10 in the 5. And they usually show constant temperature evolution, meaning they're not highly variable. Again, in contrast with AGNs, which show high variability. Okay, and let's go to the spectral properties now. So TD started being observed in the optical and UV wavelengths since 2012. Early spectroscopic work by Yair Arkavi showed that there is a continuum of helium to helium plus hydrogen to hydrogen TDs. But as more and more events started being observed, the community found that there is more than hydrogen and helium in the spectra of TDs. As you can see in this paper by Yorgos Leloudas from 2019, there is another TD category, let's say, the green ones, between the helium strong, which are the blue, and the hydrogen strong, which are the red. These TDs, the green ones, show highly ionized nitrogen and oxygen lines in their spectra. And these TDs are now called Bowen TDs by the community. And these nitrogen and oxygen lines are attributed to a mechanism called Bowen fluorescence. The emergence of these lines is attributed to the Bowen fluorescence mechanism. So let's have a look at how this heavily blended area looks like. And you can see here these two Balmer lines, like the H beta and H gamma, the classic in TDs at least, helium to recombination line at 4686 angstrom, and these two nitrogen 3 lines. This one is on top of H delta as well. But there is more complexity in the TD spectra. In a paper from 2019, collaborators of ours discovered potential iron 2 lines in this same heavily blended area, which can be associated with the formation of a compact accretion disk, or it has been attributed to that at least, especially since these lines are discovered in TDs that are bright in X-rays as well. And in another published paper, our collaboration observed these clear double-peaked profiles in the Balmer lines of TD, indicating probably the presence of an accretion disk, potentially seen from intermediate or large viewing angles, hence the double peak. So it is obvious that TD spectra are very complex, and we keep getting new insights from each individual event. This is why the community needed a systematic population study of the spectral properties of TDs, where the data reduction is done by one person in a consistent way, let's say, for all the available events. And this is something that hasn't been done so far. And this is the project that I'm currently working on my PhD. So I'm working on a sample consisting of 16 optical and UV TDs out of almost 40 to 50 discovered up to now. Or classified. It's not all of them studied, and we have set a cut to events before 2019. I will explain why. And yeah, so we can move to the data reduction part now. There were two main tasks that I had to that needed to be performed consistently for all the spectra in my sample. The first one was to subtract the host galaxy spectrum, because since TDs are in principle, they happen in the nucleus of a galaxy. The galaxy infects, let's say, the light of the transient flare. So we have to isolate the flare. And this is the reason that we set a cut to events before 2019. Because the TDs after 2019 were still ongoing, and we couldn't observe a proper host galaxy spectrum. And for example, this is an example of how this process looks like. Here's combined TD and the black one combined TD and host galaxy. The greenish one is the host galaxy spectrum. And after the subtraction, you can see that these absorption lines of the galaxy are removed, for example, and all the contribution that the galaxy gives. And yes, now the remaining, the residual spectrum is free of galaxy contribution. Yes, some galaxy spectra were pre-existing in surveys like SDSS. Else, if we didn't have the spectra, we were observing it usually with the new technology telescope in Chile, which through the IPESTA collaboration. And after the host galaxy was subtracted, the second task I had to perform was fit and subtract the continuum. And this is how such a process looks like, because we need to remove the continuum in order to isolate the spectral lines. And so I had to pick the line-free regions and fit a 3rd to 5th degree polynomial, depending on the chi-square value sometimes, and subtract it. So after this task was done as well, I could move on to fitting or deblending the emission lines of its spectrum. And this is the way to quantify its line properties. And to do so, I fitted several different profiles like Gaussians or Lorentzians, or sometimes direct integrations when no known profile matched the shape of the line. And some cases are easier to be measured, like H alpha, which in TDs is a relatively clean line, meaning it's not blended. And while others are harder, like the aforementioned, like heavily blended area, or around 4,000 to 5,000 angstrom, especially in TDs that show these nitrogen-3 Bowen fluorescence lines. And this is an example of a fit shown here. And as you can understand, this can be hard to fit, needs many constraints, and especially for a low signal to noise spectrum, this can be almost impossible to get any useful information out of. So quickly, the aims of this work is to study the evolution of line luminosities, full width half maxima, velocity offsets, meaning if they're blue shifted or red shifted from their rest wavelength, and line luminosity ratios, and study their evolution with time for each event and as a sample. And this enables us to plot these values against the temperatures and the radii of each epoch, the bolometric temperatures and radii, which are values taken from photometric studies from the literature. And in order to look for correlations between different classes, again, of TDs, for example, between Bowen and not Bowen TDs, or TDs, optical and UV TDs that also showed X-rays, or some that were veiled in X-rays. And the utmost goal of such a population study that combines the three aforementioned goals is where and how the optical emission lines are formed. Where is this line emitting region in TDs, and what's the geometry behind this structure?
Panos?
Yes.
3 minutes.
3 minutes. Okay. Okay, so I'm moving on to the results. This is the H alpha luminosity evolution, and in the 0 point, you can see it's where the light curve peaked, or where it was discovered, if it was discovered after peak, and this is the luminosity of the H alpha line, the evolution of the luminosity. And if we look closely, it looks like there is a time lag for many TDs in our sample concerning the 0 point. And from also the talk you heard before, this is seen many times in AGN studies, probed by reverberation mapping studies, where there's a light echo of emission lines in the broadline region surrounding the AGN. But these time lags here are of 7 to 40 days, which would translate to 2.5, 10 in the 16 to 10 in the 17 centimeters. And TDs have black body radii of 10 in the 14 to 10 in the 15, which sound a bit, so these values sound a bit unrealistic. Although theoretical studies like the one you see here have predicted that the H alpha photosphere would be further out from the continuum photosphere, this result would imply that H alpha is emitted 10 to 100 times further out than the optical continuum, which sounds a bit unrealistic. And we discuss several possibilities in the paper, being outflows or unbound debris, or if these lags are an optical depth effect or ionization effect. But anyway, moving on. This is the H alpha luminosity as a function of black body radius and temperature, and which are taken from the literature and interpolated for our to match our spectra. And we find that there is a clear correlation, which indicates that the larger the black body radius, the larger the H alpha luminosities, and or the opposite with the temperature. And the fact that they follow a monotonic and potentially a linear trend is in agreement with the predictions of the same theoretical study of Roth, who calculate that the smaller the outer radius is, the weaker the H alpha emission would be. Just for an event, for example, if the radius is smaller, the H alpha would be smaller. But since the photosphere recedes, we should see that the H alpha fades, which is exactly what we see for individual event evolution. And I can move on, since I think I'm running out of time. And this is the evolution, it's the last graph, the evolution of the full width half maxima of H alpha with time. And I have color coded, the blue events are the ones that show these nitrogen 3 Bowen lines, while the orange ones are all the rest, hydrogen or helium or just helium TDs. And we can see that the Bowen TDs have lower line widths, lower full width half maxima than the rest. And this is an interesting result because in a photometric population study of TDs by Van Velzen et al., they found that Bowen TDs have smaller black body radii than the rest. And so if the line emitting region is also closer for the Bowen TDs than the rest, this means that the gas kinematics should lead to higher Keplerian velocities, hence broader line profiles. So this means that the line widths in TDs are not driven by the kinematics probably. And okay, I think that's it from me. Thank you very much. If you have any questions.
Thank you very much, Panos. Yes, time for a few questions from the participants. You can raise your hands. I can start with one generic one, more of a curiosity. What is the farthest TDE that we know to date?
Farthest, you mean in terms of redshift, let's say?
Yes.
Around 0.2, I would say. We cannot, yes, they're relatively close.
What is the limiting factor for not being able to go farther? Sensitivity, maybe.
Could be. I'm not sure exactly. Yeah, I guess it's that they're luminosity. I don't know. I'm not sure about this.
Okay. Are there studies in other wavelengths that would, provide more information about?
Yes, there are. They're discovered in X-rays, and there are some jetted TDs that have been observed, and there are also observed in the radio sometimes. So this is usually is attributed to outflows, that the radio emission tracks the outer front, let's say. So the big question in TDs is the radiative emission mechanism. There is still two main scenarios, that either the viewing angle like AGNs of an accretion disk, so depending on where you look, you see the X-rays or not, and the jet maybe. The other scenario is that the radiation, the optical and UV radiation, and sorry, in the previous scenario, the X-rays are reprocessed by the bulk of the material of the debris into optical and UV wavelengths for edge-on views, while the other scenario says that the streams, like you see here, collide with itself, and where the collision happens, this is where the optical and UV luminosity is produced. So the observations in all the spectral regime are trying to put the image together and mostly support one of the two scenarios. But an interesting thing is that for a late TD of 2019, I think, there were neutrinos discovered by this. And so I guess this is a new field, but I cannot comment more about this. But I know it's a hot topic that this TD showed neutrino emission, and that can help.
Okay.
To tie the picture maybe.